Hi guys, I'm just going to briefly, okay, so now I'm going to do what's called an IVP. This is a differential equation with an initial condition. So it's a differential equation, just like the one I just showed you. Differential equation, except it has an initial condition. That's why it's called an IVP, initial value problem. Initial condition. And again, I'm going to give you an example to help you understand this. So now here's my example. We're going to start with the differential equation dy dx, and it's going to be equal to e to the x minus 5. And I know that this y contains the point 0, 2. So now I want to find the function y, whose derivative is e to the x minus 5, and it also contains that point. So what we're going to do is first we're going to do just what we did above. We're going to say, all right, y is going to be equal to e to the x minus 5x. That's easy to see. And then I'm going to add a constant. Now I'm going to use this fact right here to help me find out what that c is, because if it has an initial condition, there's only going to be one such equation with that derivative and initial point. So I'm going to put 2 in for y and 0 in for x, and solve for c, and you're going to see that we're going to get 1 plus c, and c is therefore 1. So the answer is y is equal to e to the x minus 5x plus 1, and that would be the answer to my IVP. Okay, now I'm going to give you a third type of differential equation with an IVP, initial value problem. And this one is a little bit different because I'm going to have this differential equation e to the negative x squared. This is my initial condition. We know that y of 7 is equal to 3. Now this is a little tricky because this function right here, actually there is no function whose derivative is that. So we have a slight problem here. We call this function not integrable because there is no way to find a antiderivative of that. So this is a cool way of what we do to find this function y. And what we do is we say y is equal to, and we're going to write it like this. We're going to go from 7 to x, e to the negative t squared dt, and then I'm going to add 3. And you might say, is that the right answer? Well, if you look closely here, you know that if you took the derivative of this side and this side, the derivative is, in fact, of this going to be e to the negative x squared. The fundamental theorem of calculus says so. And the derivative of 3 is 0, so it goes away. So this is true, that this function right here, its derivative is this. And you can also see that if I put 7 in for x, 7 to 7, the integral would be 0. That's a definite integral. And then we would add 3, and we would get this initial condition. And so there it is. This is another way of writing the function y, whose derivative is that, the answer to this differential equation. Okay, now we're going to talk about section 7.2, which is integration, antidifferentiation by substitution, another way of integrating. So now I put a new picture in here. This one is again me, and you can see that my hairstyle again has not changed much, and you can also see how my fashion sense is, was developing back then. It's probably very similar to how it is now. Anyway, so here we are. We are going to learn integration techniques now. Integration techniques. And you remember when we were taking derivatives, we learned rules for differentiation. Well, instead of the rules, we're going to use techniques to try to figure out what the answer to the differential equation is. So I'm going to start out again by an example. So what we need to do is we're going to try to solve this integral. E to the x times cosine e to the x times the sine cubed of e to the x dx. Okay, so in other words, this is an indefinite integral because it doesn't have the a and the b. You can see going from here to here. This is just asking me give me a function whose derivative is this, and that's what an integral is. So we have to use a technique to do this, and the technique that I'm going to teach you right now is called the substitution technique. So what I'm going to do is I'm going to go over to the corner and make a box, and I'm going to do some work in this box and then use the box. If you'd like to, you can decorate your box with flowers or whatever you want to decorate your box with. I'm going to make a little flower. Okay, I'll make a little flower over here for this box. And now I'm going to show you how we fill it in. So what you want to do is you're going to look at the equation and try to pick the most complicated part of it. And right here you can see that is, because that's sine of e to the x cubed. So I'm going to take that and I'm going to use in a different variable, u, and I'm going to say, alright, let's let u equal, I'm picking that most complicated part, but just inside it, I'm going to let u equal sine of e to the x. Okay, so you pick something out. You might pick the wrong u and then go about, and you're going to have to go back and do it again, but that's all. That makes this kind of a fun thing to do. You might get it wrong, but you got to go back. Then what you're going to do is take the derivative of both sides of this equation with respect to x. So this would be du dx is equal to, and the derivative of sine e to the x would be cosine of e to the x times e to the x. Okay? Then if I look back in this, I see that I have a dx there. And that's what I want to substitute back in. This is called the substitution method. I'm letting u be something, and then what I'm going to do is solve this equation right here for dx. So I'm going to just do a quick swap. You can see like this is almost over 1. I'm just going to basically swap those two positions there, a little algebra move. And I'm going to say, alright, well then du over the cosine of e to the x times e to the x will equal dx. Okay, just a little simple algebra there. And that's what I'm now going to go back, take my box, and I'm going to go back into this equation. So I'm going to go back and I'm going to rewrite this. Alright, it's e to the x still, and then I have a cosine of e to the x, and then instead of sine e to the x cubed, I'm going to make that u cubed, because I'm using this substitution right here in for the sine x. Okay, so I'm going to go back in here, and then dx, you can see, is equal to this. So instead of writing dx, I'm going to put that in there. So I'm going to put du over cosine e to the x times e to the x. And then you guys can see, voila, I can do a little math here. Well, these cancel out. That's 1. E to the x over e to the x is 1. And what I'm left with is u cubed du. Ah, this is an integral I know how to solve. So I am going to write this as u to the 4th over 4 plus c, because I know that there's many different functions whose derivative will be that. And then the only thing I have to do, remember, is to go back and put what u was. Well, u was sine e to the x. So we're going to take that, raise that to the 4th power, divide by 4, and add c, and that is the solution. That is my y. That's my function, whose the derivative is this right here. Before I give you, the last example here, I want to point out that on page 337 of your book is these properties of indefinite integrals, and then some indefinite integrals that you can definitely see for yourself that would be true, and they're all right there in your book. But the antiderivative, the integral of cos u du would be sine u plus c, because the derivative of sine is cos. Anyway, these are good to refer back to. You can look at any point. Okay, finally, one last example of how to solve an indefinite integral using substitution technique. And so I'm going to give you this example right here. The integral of 3x squared minus 5 times the square root of x cubed minus 5x dx. Okay, again, we're going to go over and we're going to make a little box to the side, and we're going to pick a u that we want. And this is the tough part, but you'll get better at it. And like I said, you kind of look at the most complicated part. It looks like maybe this is more complicated, and inside this is this x cubed minus 5x. So that, in fact, is what I'm going to pick. I'm going to let u be equal to x cubed minus 5x. And then I'm going to take the derivative of both sides with respect to x. Du dx would be 3x squared minus 5. And then I'm going to notice, aha, that's something that's in this original problem. You can see right here. So, and then I'm going to solve this for dx, because that's what I want to substitute in. So I'm going to do a little math, a little algebra there, properties of proportions, and switch these two. And that will have to equal dx. And now I'm good to go and go back to my original equation. So I'm going to go back here, and I'm going to rewrite, that's what it says, 3x squared minus 5. Didn't make a u substitution for that. And this would be the square root of u. Okay. And then the dx is du over 3x squared minus 5. And then, voila, I can see that these will cancel. And what I'm going to end up with is the integral of square root of u du. And I can solve this. I'm going to rewrite this just to help myself out, because this is u to the 1/2 du. So I'm going to use that property from page 337, one of those properties right there. And I'm going to solve this integral and say that it is u. I'm going to take, whoops. I'm going to take, it's going to be u, and 1/2 plus 1 is 3/2, and if I'm over 3/2, if I'm dividing by 3/2, I'm multiplying by 2/3, and then plus c, and there's the answer to my integral. But I just have to remember to go back and put what u was. So this is going to be 2/3, and I'm going to have u is 3x squared minus 5, and I'm going to raise that to the 3/2 power, and then add my constant. And that's it. Okay, guys, have fun. See you tomorrow.